Hello everybody, this is Dr. Christopher White, and in this video we're going to be looking at how we explore for groundwater. So the first question to be addressed is, well, why are we so interested in groundwater? And the obvious answer to that is groundwater is a very useful source of water for residential uses and for farming uses. So knowing where it is and how much of it there is extremely helpful. Another reason that we want to know about groundwater is it helps us to model lakes and rivers. So if you're dealing with a situation where you know you have gaining streams and gaining lakes that obviously have a groundwater input, modeling for those bodies of water is going to have to include that groundwater flow information. We also want to know about the groundwater for reasons of pollution. So if we know that there is pollution that has occurred in an area and that pollution is likely to have infiltrated down into the ground and possibly down to the water table, it will be extremely helpful to know where the groundwater is flowing so we have some kind of idea about where that pollution could have gone. So next we're going to think about how we study groundwater. So the study of groundwater is going to be undertaken by a specialist type of geologist called a hydrogeologist. And they are going to begin by collecting information about the topography of an area, any geologic maps about that area, any geologic reports about that area, and any previous hydrogeological studies. So any work, for instance, on boreholes, water quality, or maybe water table height. And that's going to give them a starting point for the study of their area. Now, if the area is or it has limited data or no data about it, the hydrogeologists will have to undertake field work to get a better idea of what's happening in the subsurface. So they might have to go out and map rocks, they may have to look for structures, they may have to take water samples, etc. And so this is going to give them some idea of what's happening to the rock layers underground. Now, due to surface water and groundwater being so closely interconnected, hydrogeologists will collect data about surface water as well. So they're going to look at things like the discharge of rivers, they're going to look at the water chemistry, because obviously this could affect groundwater or it could be a reflection of the groundwater. And they're also going to do longer term analysis. So they're going to try and work out, are these streams, are they gaining streams or losing streams? Because once again, that's going to control how much of an interaction these bodies of water are going to have with the groundwater. Geologists will also use boreholes, and they will be used to measure the height of the water table using what's called a water table indicator. And this is a device that is passed down the borehole, and it uses either electric currents or sound to measure the transition from unsaturated to saturated zones. And so by using it, you can define the height of the water table. And then we will also be collecting borehole water samples, and this will allow for checks on water quality. It will allow geologists to measure the rate of infiltration, how quickly water enters the borehole, and it will also allow for groundwater flow to be mapped using dyes. So if you have a situation where you have several boreholes in an area, you can put a biodegradable dye down one of the boreholes and you can monitor the other boreholes to see how quickly that dye appears in the water located in that borehole. We may also undertake pump tests down these boreholes, and these will be undertaken to measure the rates of recovery, so how much water can you take out, and also rates of recharge, how quickly will that water refill to the same level. And obviously this is going to be important when it comes to extracting water for things like residential or farming use, because you don't want to be removing water faster than that water in the borehole can be recharged. Otherwise, you're going to have a net loss and you're going to be essentially exploiting your groundwater too much. Now, hydrogeologists may also undertake geophysical surveys, and these will be used to image the subsurface. So when it comes to geologists going out into the field and mapping rocks, you can predict where certain layers of rock are going to go. However, it's not an exact science. And so, in a lot of instances, using geophysics is helpful because it really allows you to outline where each layer of rock is going, and so you have a much better idea of what's actually going on. So in terms of the methods used, they may use seismic reflection data, they may use gravity, magnetic or conductivity information, and this is all going to be used to essentially assess the geometry of the layers of rock in the subsurface. So where are the rocks dipping, what angle and in what orientation are they dipping. They're also going to be useful because they will allow you to pick out porous layers of rock and sediment within your sequence, and they're going to be useful as well because some of the methods will also allow you to identify layers of rock that contain groundwater. So all of this information can be gathered from geophysical surveys, and obviously it's a lot of very helpful information to better understand what's going on, especially the geology. Now, once you have the location of your porous rocks and sediment, you will then drill boreholes to collect samples through your sequence. So you're obviously interested not only in the layer of rock that contains the groundwater, you're also interested in the layers of rock above it. So the most basic question is the aquifer confined or unconfined? Is there an impermeable layer above it? You're also going to want to know things like, well, how thick is the aquifer? What type of rock is it made from? How porous and permeable is that rock? Because that's going to control how much water the layer can hold and how easily that groundwater can flow. And the only way to get this information is to take direct samples. Drilling is also going to allow you to see if there is more than one aquifer in an area, because it's not uncommon during drilling for you to discover that, right, there's one aquifer in this layer, then as I go down a bit further, there's actually another aquifer, and there may be several aquifers stacked one on top of another. And the best way of finding this information out is by drilling a borehole. There is a caveat though. Borehole drilling tends to be expensive, so it tends to be something that's done relatively late in the study once you have a whole load of information from other sources, because you don't want to waste money putting a borehole down in an area where you're not going to get any useful information. Now, these boreholes, as mentioned, can offer us a lot of information, especially the position of the water table. It allows us to measure the height of the water table. It lets water samples be collected, which is very important because we obviously want to know what the water quality is. And it allows the aforementioned pump studies to be undertaken. How much water can you pump out and how quickly will that water be replenished? You can also put cameras down the boreholes, and these cameras will allow you to look at the layers of rock and sediment within the borehole, and it will also give you an idea about the aquifer itself as well. So after you've got all this information, geologists and hydrogeologists will use these subsurface studies, the geophysics and the boreholes, and they will use that to produce a stratigraphic column for an area, so you know what layers of rock are there and also which of those layers are porous and possibly groundwater bearing. You will have obviously your geophysical information that will allow you to allow you to visualize where those layers of rock are going, and also visualize any structures that might exist in the subsurface like folds or faults. It will obviously give you the permeability information, and this will also allow you to look and say, right, which of these layers of rock are most likely to act as aquifers based on how porous and how permeable they are. So all of this information is going to be collected, it's all going to be put together, and it's going to be used to essentially say, right, this is where the water table is located, this is its geometry, and this is how quickly water is moving from point A to point B. So once we have all that information, how do we actually start to depict it so it can be used by people? So if you look in the top left here, we have the standard borehole map, which is presented a lot in hydrogeological reports. So the map itself shows you the topographic map for an area, including buildings, roads, etc. And typically there will also be contour lines on there as well. And you will see that there are several borehole locations or well locations which are marked out by these blue dots. And next to each of these locations, there is a value which is giving the height of the water table typically in meters, sometimes in feet. Now, obviously, in order to find out which, you need to read the key for the map. So each of these is giving you the elevation of the water table at that borehole or well. So once you have this information, you can, just like a topographic map, draw contour lines of equal elevation. But in this case, it's not the surface of the earth that you're drawing the contour lines for, it's the surface of the water table. So if we look at our map here, first of all, you will notice that you have higher values in the northern portion. You've got 140 meters and 150 meters here. And as you come towards the south, the numbers are decreasing to 110, 109. So clearly the water table is dropping or is sloping downwards towards the south. Now, in terms of drawing the contours, what you're going to do is you're going to try and find points of equal elevation. So for instance, here we have 130 and here we have 130 as well. So clearly a contour line is going to come down like so. The contour line will obviously have to pass between 129 and 132 in the middle between them. So we know our contour line is going to come through like that. In terms of the 120 contour line, well, we can see we've got a point here. We also have 119 here and 129 here. So we know that our contour is going to be passing just to the north of the 119. So we're going to draw our contour line coming through here like so. In terms of the 110 contour line, we have a point right here. We have 109 here. So we know 109, 120. We know our contour is going to be about here. Well, that's going to be the approximate position of 110. And so our contour line is going to come through like so. And so we're going to use this groundwater elevation data to produce contours. And these contours are going to give us a visual representation of the geometry of the water table. Now, once we have this information, so we can say, right, the water table is essentially the elevation's dropping as we head in this direction. This is going to give us a good idea about the flow of the groundwater, because groundwater will flow down the water table slope under gravity. And so this means if we're referring to our map here, we know that we have our higher water table elevation up here and a lower elevation down here. So we know that the water is going to be going approximately from the north down towards the south. Now, when it comes to these contour maps that are produced by hydrogeologists, they will also typically include arrows on them, and these arrows actually are showing you the direction of groundwater flow. So on this map here, you can see that there are 3 arrows marked out in blue, and you will notice, and this is most important, the arrow position is at 90 degrees to the contour line. And if you follow that rule, so 90 degrees there, 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 and there, it produces, in this case, this slight curve to the arrow. And so this is very important if you are drawing a hydrogeologic contour map like this, then you have to have these arrows at 90 degrees to the contour lines in order to actually accurately predict where the water is going to be flowing. So once we have all this information about the elevation of the water table, what are we going to do from there? Well, hydrogeologists will take this water table elevation data and they will combine it with subsurface information, and they'll use that to produce a model for the water table in 3 dimensions so we can better understand the geometry. So in this case, you can see we have here is our contoured water table elevation map. Here is our surface topography. And using these 2 overlaid, essentially you can track to the same contour lines here are being projected onto this diagram here. And so you can predict where the water table is going. And straight away you can see in this instance, the water table is dropping in elevation as you head towards the southwestern corner right here. And so once again, on your block diagram, you can see you're heading down towards the southwestern corner. There, the elevation is coming down. And so this is a visual representation of what is happening in terms of the water table elevation. Now, it's worth pointing out that along with this information from the boreholes, they will also combine it with other information, for instance, rivers and lake positions, because these will often cause changes in the elevation of a borehole, especially if that river or lake is a losing stream, so it's contributing water to your groundwater. You will often see a localized elevation of the water table underneath those features, obviously because water is being added from the river or the lake, and so this is going to cause the water table in that area to come up. Conversely, if you have wells which are removing water from the groundwater, well, that's going to produce what's referred to as a cone of depression as water is funneled into the borehole by the pump. And so all of this additional information is going to be added to this model, and it's going to allow you to produce a generalized but still quite accurate map of what's probably happening to the water table in your area. Now, what you can then do once you know what's happening to the water table is you can then take that information and you can apply it to a three-dimensional model of the geology of your area. And so those things combined can essentially give you a schematic geologic model. So it shows you each of the layers of rock in the subsurface, but it also shows you the position of the groundwater relative to those layers of rock. And so it lets you see in the subsurface, right, these are the layers of rock that contain groundwater, because remember, the groundwater will often cut across different layers of rock. As long as they're permeable, the groundwater will move through them. But it will also allow you to better visualize where the impermeable layers are and how they are affecting the flow of groundwater in the subsurface. Finally, if you are going for a really detailed analysis, you will produce what's called a high-resolution three-dimensional computer-generated model. And this is going to combine a lot of information. So it's going to include things like the surface topography, the subsurface geology, the water table elevation data, borehole locations, stratigraphic columns from those boreholes. A whole load of information will be put into this computer model. And this is going to produce a very high resolution map of what's happening with the groundwater. And this is important for select situations. So it's very important if you are trying to select an area for groundwater extraction, for instance. So obviously you want to, select an area where the water table isn't too deep, because obviously the shallower it is, the cheaper the borehole will be to drill. But at the same time, you want to also pick an area where you know there's going to be good water flow to replace that water that you are removing. It's also going to be important if you want to track contamination. So, for instance, let's say there is a site in your area which is leaking toxic chemicals into your groundwater. You're really, really going to want to know where that contaminated water is going in the subsurface. And so these high resolution models, they're not commonly produced, but they are produced when you need them. So for instance, a municipal water supplier who is pumping out groundwater would definitely need one of these models to try and ensure that they pick the best location for their borehole, whilst also not causing significant damage to the groundwater, the aquifer itself. Okay, thank you for watching, everybody.